Hey chat, welcome back to another video. Today I'm just going to be going over some sampling frequency practice. So just a few questions on if you were to sample a function, what sort of sampling frequency would you need to sample? So yeah, let's get into it. The first sort of important note here, sorry, let me just move this equation over, is that you want the sampling frequency, or fs, to be more than 2 with the max frequency. And the reason as to why this is, I think can be best explained with a sine function. So if you have a sine function, like this here, sorry it's a bad drawing, but you know the frequency is from this point here to this point here. That is the frequency of the sine wave. So first off, you want to have at least 2 times the frequency max. And this is because if you're looking at a sine wave, you can notice that if you don't sample at 2 times the max frequency, you may miss the down part or the upper part of the wave. So you could just sample this part of the wave or anything. And then if you're looking at 2 times the frequency max, you might get samples from points like this. Just mark there. So the reason you want 2 times the max frequency is because sampling at exactly 2 times the max frequency will give you these points here, which can be all 0 valued. So to avoid this, you want to instead sample at a frequency at least slightly larger than your max frequency. So you end up with points like this, let's say, and doing this, you will be able to actually reconstruct the function because you'll get actual values that will match up with the sine wave. So yeah, let's just get into the questions then. So if we're looking at this first question here, it says determine the conditions for Ts, which is the sampling period, so that this function can be perfectly reconstructed. Now looking at this straight up, it's sort of, you can tell that it's sort of impossible to tell what the max frequency of this function is, because you have a sine function times a sinh function and a cosine function times a sinh function. It's sort of hard to imagine what this would look like. So when you have something like this where you can't just tell the max frequency straight off the bat, what's best to do is to first try and convert this into a Fourier transform. So looking at my own Fourier transform equation sheet here, I can just write these down. You know that, I'm just going to erase this quickly, you know that cos 2 pi f naught t will change into, with a Fourier transform, 1/2 plus the impulse f plus f naught. And then the sine one is okay. So those are, whoopsie, sorry. Those are sort of the Fourier transforms you will end up with. And for the sinh functions, you know that the sinh function, with a Fourier transform, it will just transform into a rectangle function. So if you look here, we can easily apply this to this function here. And the other notable one is that if you have a function, the other notable thing here is if you have a function gt times h of t multiplied, that Fourier transform will turn into g of f convolution with h of f. So using what we know here, we can then actually go ahead and start solving. So we're looking for the Fourier transform of x. You have 4 multiplied by, it'll be the Fourier transform of the sine function, which if you look here, you can see that f naught will be 2 because you factor out 2 pi from 4 pi. You're left with 2 times 2 pi times t. So f naught will end up being 2. So this can be written as 4 times j over 2 times the impulse of f plus 2 minus the impulse of f minus 2. And then that is convoluted with this rectangle, or the sinc function here, which the Fourier transform for the sinc function, as mentioned before, is just rect f. So that's what you'll end up with for that one. And then next, you can do the convolution, the other terms. So plus 2 times 1/2. And then once again, using the same strategy here, you look at 8 pi t, and you look at this convolution here, you can see that f naught is 4, because this is equal to 4 times 2 pi times t. So you can do that. F minus 4 plus the impulse of f plus 4. And that's going to be that convoluted with sinc, which once again just transforms into the rectangle f. So now you're left with these equations here. You can pretty much simplify it, because if you're looking at a convolution of if you're looking at the convolution of an impulse function to another function, like a rectangle function, like a sinc function, and you convolute them together, basically what you end up with is just that whatever function is being convoluted with the impulse function is just shifted over to wherever the impulse is. So we still have 4j over 2, but when you convolute this rectangle function with this impulse function, basically this rectangle function will just be shifted to these frequencies, minus 4j over 2 rectangle. Or actually, this can be just written as 2j rectangle f minus 2, and then plus rectangle f minus 4 plus rectangle f plus 4. So through doing this, we're left with these rectangle functions. And you can pretty quickly, if you were to imagine these rectangle functions, I think the best way to do it is to just draw them out and to visualize them. So if we were to draw out these functions, you have a rectangle at -2. Let's just say -2 is here, at -4, at +2, and at +4. And well, the exact height of these rectangles doesn't really matter. You're really looking at the frequency. So if you have a rectangle centered around 4, it goes to 3.5 and 4.5. You have one here. They have different heights, obviously, but it's not as important. And 2.5. And you have a rectangle center in here, -2.5, -1.5. One more rectangle here, -4.5, -3.5. So you're left with these rectangles. Again, the height of these doesn't really matter. We're looking at the x-axis, which is the frequency. And looking at the x-axis, you can tell that the maximum frequency is going to be 4.5 or -4.5. So if we're taking the sampling frequency, it has to be more than the 2 times the absolute value of f max. We're going to get the sampling frequency is more than 2 times 4.5. So we end up with the sampling frequency is more than 9. The question initially asks what the sampling period would be. You know that frequency is just equal to 1 over the period. So you get 1 over the sampling period to be 9. Then you get the sampling period has to be less than 1 over 9. So that's your final answer there. For a question of this sort, where it asks for the sampling frequency or sampling period so that a function can be perfectly reconstructed. So we're just going to do one more example here of finding the required sampling frequency. As you can see here, I've already written out some of the important Fourier transforms, which is that a sinc function Fourier transforms into a rectangle function, the rectangle function Fourier transforms into a sinc function, and this property here, which is important because as you can see here, we have values for a in both of these functions. So if you were to start off and do the sinc function, first we can do the Fourier transform of that. And you get 1 over 100 times the rectangle of 1 over 100t. And for the rectangle function, you do the same thing. The Fourier transform, you 1 over 200 sinc 1 over 200t. So using these and knowing the property that a convolution, when doing a Fourier transform, a convolution becomes multiplication, you can put these together and you have, it'll be 1 times 20,000 because you're multiplying 1 over 100 by 1 over 200, rectangle 1 over 100t times the sinc of 1 over 200t. Now the important thing to note here is that once again at the start, it's sort of hard to, with this sinc 100t times rectangular 100t convoluted, it's basically impossible to figure out what the maximum frequency is when you're convoluting these two. It's hard to figure out. So that's why we actually in the first place did this Fourier transform, to try and make it easier. And looking at this, once again, it's hard to find not hard to. You can find the maximum frequency of the sinc function, but it's going to be very large. But what's important to note here is that the sinc function frequency will actually be limited by the rectangular function frequency. So if you were to draw out the rectangular function, when it's just 1 unit, 0.5, 0.5, and 1. But with this, you have this 1 over 100, which, if you think about properties of a function, when you're doing this 1 over 100, you're actually stretching out the function by 100 times. So what will happen is when you have rectangle 1 over 100, what you'll end up with this. is with this. Negative 50, 50, and 1. And anything past this plus 50 or this minus 50 will actually end up being 0, and that's even with the sinc function. So the sinc function is limited by this frequency of the rectangular function, because even past the frequency of 50 where the sinc function might have some sort of value, since the rectangular function is 0, the overall function will be 0, since 0 times whatever is still 0. So because the entire function is basically limited by this frequency, you know that the f max is equal to plus or minus 50. And using this, you can solve for the sampling frequency, which once again has to be more than 2f max. So the sampling frequency has to be more than 2 times 50, and we know that the sampling frequency has to be more than 100 hertz. And that's sort of your final answer. Sorry, I need to scroll down there. But that's sort of your final answer there for how to solve the sampling frequency to perfectly reconstruct a function. So yeah, those were 2 examples on how to solve for sampling frequency and period of a function when you want to perfectly reconstruct it. Let me know if you have any questions in the comments. Please like and subscribe. Ferg Iceberg out.